Hey, so everyone, welcome back. I think there's some information a lot of you will be interested to know about the homework. I've had a few requests for extensions on the homework. I asked last week, I'm like, I don't know, this is all, you guys only have like a week and a half to do. Is that okay? You're like, sure, that's fine. And so now everyone's like, well, I could use a little bit more time. So I'm okay extending the deadline but I know when I was a student, sometimes I had it done, and I'm like, all these other people, they're asking for deadlines, and I worked really hard. So if most of the class does not want an extension, I might be less wanting to do it. So I thought I would ask the people who came to class. So for those, if you want an extension. So I was first thinking of Friday, but then someone said there's people traveling until Friday. So I was thinking either to have the homework due on Saturday. Is like 5 p.m. better, or would you rather do it at midnight? I know midnight. You want to do midnight on Saturday. All right. So I always like it 5 p.m. because then you're like, all right, now I can go eat dinner and relax. But what?
All the other times are always doing midnight.
Okay. All right. Okay. So let's. Okay. We'll have two options. We're gonna vote by show of hands, and so I'll take Ankit to vote for whoever is on the other side. So who wants to keep the deadline as is and do on Wednesday at 5 p.m.? Okay. Okay, and who wants to do Saturday at midnight? All right. It will be Saturday at midnight by, I'm not even going to count. That was basically everyone. So, okay. So as long as we're on the homework, I thought we might as well. Like 5 people left now that the assignment got extended. They were so excited they had to yell and joy. So they just came to vote. I thought there seemed to be a lot of questions about this homework. I've answered some on Canvas. If there are any other things, please ask now. Yeah.
So there's this. I think the questions they ask us to compare similarities of assignments, subsets.
Yeah.
And there was a discussion whether we're reporting only centers or also the phi's, like the percentage of phi or the percentage of assignments that belong to the same center.
Yeah. So the question was. So the question was. There's some points. I think this is for question 2A. So supposed to report. So this was this 2A. Report fraction of k means plus with the same subset as the Gonzalez algorithm. And so sometimes it'll have the same centers, but that's going to be pretty rare because k means plus is going to be fairly random. But they may end up having the exact same points mapping onto the centers. And so I think this will happen roughly 10% of the time. I forget. I haven't don't remember the days. Maybe probably between 10 and 20% of the time, they will have roughly the same centers, not exactly the same. Is it smaller than that?
Well, is center the same or the clustering the same?
The clustering. So actually I've done this similar assignment in the past, and we had smaller data sets. So maybe with the bigger ones, it's less likely. But I want all the points to be assigned to the same center.
Yeah.
Not the same centers.
It's asking the subsets are the same.
Yeah, so I want the subsets. So if it's possible, I haven't run the code myself to check, right? But it might be like 0. Do you have? It's pretty small. It's pretty rare.
If you're lucky, you get.
Okay. So then it might be pretty rare. But I want you to check. Okay, I want the exact same subsets.
Okay.
Yeah. So yeah.
So we're just saying this cluster is the same as this cluster in both algorithms.
Yeah. So basically, you have this data set C2, and you're going to have clusters C1, C2, and C3, and for all these points, right, you're going to map some onto this one. And so all of the points are going to map to one of the centers, and it's going to decompose it into 3 sets. And I want if those sets exactly align with the same 3 sets from Gonzalez. So I guess it's fairly rare, but so often it'll be close, I guess, but it'll be rare to be exactly the same. Yeah. Any other questions about this? Okay, so feel free to post more questions on Canvas. I'll try and clarify stuff. So, okay, so the other thing that's coming up is going to be there's 1 week from today we're going to have a quiz. I called it a quiz because it's not a huge fraction of your grade. I don't want to call it like a midterm or something. It's only like for each quiz is 5% of the grade. So I don't intend this to be too hard. As always, some people will take the full class to do it, but some people will finish fairly quickly. It's going to cover everything up through the frequent items section, okay? And then everything after that, which is starting from today, will be covered on the second quiz, okay? And I say it's covering all that, but it can't possibly cover all that. I'll pick out some questions which you can do in class. It's going to be open book, and open computer, but I don't think the computer will help. The one thing, so I have to, this is a compromise where I have to trust you guys. So I don't need you guys to print out all of the lecture notes I wrote up because it's a lot of paper. But the thing I don't want you to do on your computer is chat or communicate with other people during the during the quiz, and that's hard to enforce. So it's going to be some trust. If we see that any sort of communication, we're going to be very harsh on that, and we'll be kind of sneakily walking around just when you don't suspect it, looking for that sort of thing. So you can't do that. But you can look at resources online. I don't think you can write code if you want to. I don't think that's going to help you. But the questions are things you should just be able to do pencil and paper. It may sometimes be useful to look at the notes. So and I don't want you to have to print all of them out. I think that's kind of silly. So I'm going to allow you to use your computers. Okay, that seem fair? Okay, but if we catch you doing any sort of communication at all, even if you're done, if you're going to go do that, go outside. Right? Otherwise, you're going to get a 0 for the whole quiz. So we just that's the one thing we can't let you do. Okay, so just a couple other scheduling notes. So there is the next homework is on the frequent item stuff, and we finished all that material already. So we're going to try and post that homework this week. It's not due until the week after break, but we'll try and get it out. That one is going to be much shorter. So homeworks 4 and 6 are kind of worth up to 50 points. So these are shorter homeworks. Homework 5 is again worth 100 points again, but I don't think it's going to take as long as the first 3 homeworks. But it'll be roughly the same length and style. But homeworks 4 and 6 should be shorter, so they shouldn't be as bad. So hopefully, after this one, the bulk of the homework should be done. But you guys should then be going in on your projects more deeply. And then the intermediate report is due the day after break. So you should kind of get going on that. I want see some partial progress on how you've done. You should have done the basics of what you want to do for the final project. And the point is so that I can give you feedback on how to finish the project appropriately. Really, I want you to see you've made progress so I can tell you how to help finish it in a way that's good. Yeah, question?
I have a couple of questions of the homework.
Okay.
Well, first I was wondering in Lloyd's algorithm, when you kind of create a new center for whatever round you're on,
Yeah.
you treat that center as one of your data points, or you treat it as like virtual points in the data, and you don't let it affect your results.
Yeah, so the question is, in Lloyd's algorithm, the new center points, do they need to be part of the data, or how do they work? And so in Lloyd's, the centers can be anywhere. So Lloyd's is going to have the centers are going to be anywhere in RD, right? So it can be any. It doesn't need to be one of the data points. And this is an advantage and a disadvantage. The Gonzalez and K-means plus, they only gave you elements of your data set. This allowed them to run more easily and actually more generally. Sometimes your data is not in RD. Lloyd's, you assume it's in RD, in d-dimensional Euclidean space, essentially. This means you can get a smaller score. The centers do a better job of representing because they're not restricted to be the data points. But then if your data is not in Euclidean, are not Euclidean vectors, you can't really use this. So it's kind of a trade-off there. So they're not in they aren't in the data set, so they're not restricted to the data, and so they don't affect the score. When you do a sum, right? When you're doing the cost 2 of your data set and the centers, and you do this sum over, was this an S? What was it? Let's say P in P of the distance between P and the closest center squared. This summation is only over, this is the data. It's not over the center. And if you did have it in here, this would be 0 anyways. So it wouldn't really affect it.
Yeah. Also, so at each round you try to find a new average point, which will then become your new center. And there's a formula in the notes that I was wondering, is it the same as just taking the sum of all the x's and taking the average of that, and taking the sum of all y's and taking the average of that, and using that point? Does that formula equate to that?
Yeah, so the question is, in the Lloyd's step, there's this separate, you have to take the average of a set. So you have the new center as the average, and let's call this PI, and these are all the points which are assigned to the old center CI, right? And so so there's this really nice property of the average that you can take the average of each coordinate, and then so the x coordinate, take the average of the x coordinate of all these points, that's the x coordinate of the center. So this is the same thing. This is true for the average if you want to do something, and as you'll see in the third part of question 2, this average minimizes the sum of square distances. This is a really important fact, right? And this is not necessarily true for the sum of distances. And so it's not clear how to create the new center if you're doing the sum of distances, which I'll ask you to do it in part 3, in question 3. So question 3, there's an obvious way how to do it and get an okay score, and that'll give you most of the points. If you improve upon that, we'll give you more points. Yeah.
What was phi sub z?
So phi sub z is the arg min phi sub z of p is equal to the arg min over the centers. So these are over the set of centers. It's the distance from p to the center. So it's the center which is closest to the data point. The minimum returns the value. The arg min returns the element which minimizes this function. So it returns the closest center to the point P. So this tells you the assignment. So it's assignment-based clustering. This defines the assignment. Okay, great. So we'll, any other questions, just ask them on Canvas, or again on Wednesday, I guess we have time. So Okay, so enjoy your Friday and Saturday nights doing my homework now. It's your choice. Okay. All right, so today we're going to start kind of a big new section of class. Kind of probably up until 10 years ago, the two main things associated with data mining were going to be clustering and some form of regression. These are kind of two basic ways of doing, so kind of finding structure in data. Now we'll talk about these graphs, which has kind of been a new, interesting evolution. That'll be the last section of class after doing stuff in regression. We're starting this new section in regression, and kind of this is a fairly general area. Basically, if I define this in a way that's very general, the idea is you have and so if you're taking the machine learning class, you'll see some similar ideas, but you'll start with some data, and we'll call this X, and you have a class of sort of shapes that you want to fit to the data, and then you want to find so you want to find f star, which is the arg min of all the shapes in your function class that somehow minimize some error between data and f. Okay, so you kind of think of, you have data, you want a shape that you want to be close to this data, right? So clustering, the assignment-based clustering was kind of like this. I said my class here was if it was a 3 centers I could choose, then the class was any 3 data points, and the error was either the k-means cost or the k-median cost or the k-center cost. This is kind of one class here. The most typical way to think of this in regression, though, is when your data, let's draw the data here in blue, looks kind of like, think of them as points, and then your class F, so these are often, think of some lines. So you want to find a line. It should be a straight line, if it's straight enough. It should be a perfectly straight line that goes through the data, and you want all the data to be close to this line. Instead of being close to points, you're closer to lines. In general, you can think of this, if you're in higher dimension, you can either again say it's a line, or you can think of it like a subspace. So if you think of these points are floating around in RD, right, in R3, so they're all up here somewhere, and then I want to, like a plane that goes through them, and I want to be close to that plane. You can generalize this higher dimensions, okay? So we'll kind of talk about these generalization, and really, this is a really useful way to help you think about what's going on in high dimensional space. Thinking about these algorithms, because they have nice kind of, they're mathematicians have found a way to relate them to other parts of math, namely matrices, which we understand pretty well. So the goal today is just to talk about this in R2, so in 2 dimensions. Okay, so this will kind of be a preview of the next like 4 or 5 lectures, kind of telling you what's going on in these, so just in these 2 dimensions. And so you can kind of see most of what's it'll allow you to kind of see a bunch of different techniques compared against each other, and then we'll go and develop them. And most of them are actually more interesting in higher dimensions. But you kind of see what happens mainly in 2D. Okay, so to start with, let me use this picture to kind of give a preview of the rest of the preview. You can kind of think of the most common way to think of this as the least squares is often what's called. So there's a least squares regression, or this is called just ordinary least squares. And the idea is, for every point, you want to draw a vertical line down onto the black line. And so each of these, and you do this for all the points, and so this line is called this line is called the residual. And you can think of, for a point here, P, and so onto this line, you can mark this point L of P. And so then the cost of the residual is then going to be P minus L of P. Okay, this distance here. And so typically, so the least squares means that we want to square this distance, to square this residual, and we want to, it's a plural, so we're going to sum over all of these. So we have a data set P. We're going to sum up these squares of these residuals. And we want the least squares, so we want to minimize this. We want to find, so this error now is defined as the sum of the squares. Sometimes it's the average of the sum of the squares, but that really has the same minimum, and we only care about the argument of the minimum, so it's the same thing. Right? So we want to minimize the sum of these squared distances of the point onto the line. And so this is the least squares formulation, and this is the very common way to solve it. It turns out there's a very simple closed form way of doing this, actually. So we want to find the line, this line L, which minimizes the sum of these squared distances. Okay, and as we'll see, this is, not the only choice. For instance, why is it the sum of the squares? Why not just the sum of the distances? Or why measure the vertical distance instead of the closest point is over here? This green point is closer to P than this point. Why are we using this vertical distance? So there are kind of some, the answer doesn't necessarily end here. Okay, so let's go and try and formulate this a bit more carefully. Okay, so linear least squares. So, and again, to simplify things, I'll describe this in 2D, and then I'll mention how it generalizes to higher dimensions and these other settings. But we'll think of, we're going to have a data set is going to be P, and this will be in R2. But this is such that we're going to have data points P1, which is going to have so P2. Say they're n data points, and so we can break this into two coordinates. We'll call this px and py. So we'll have the x coordinate of each data point in this vector and the y coordinate here. So for instance, if I drew axis here, this is, say, if this is p1, then I can say this is equal to, the x coordinate may be 3 and the y coordinate is 1. Right? So then, if I looked inside of this vector, this would be, the first element is 3 here and 1 here. Okay. So I have these two vectors now I can think about. So now, again, we want to find a line, a line which is going. Let's not draw it there. So we want to find, say, a line which is going through all these points. And how do we simply describe a line? We're going to do, the first thing is the slope is going to be, so A is going to be the slope. Remember, this is the rise over the run. So if I move at a vertical distance of 1, how much does it go up here? And this looks like the slope is roughly equal to 1. And then the second one is B is going to be the intercept. And even though I tried not to draw this through the origin, it's pretty close. But let's say in this case, it's going to be something like 0.5. Okay, so 0.5 is the intercept, and then my line I can describe for any value x. It's going to give me a value y, and in this case it's going to be b plus a times x. Right. So now this describes, this blue line is described by these two coordinates, these two values b and a. So if I can find the values b and a, I've found this line. Right. So now, given a data set, I need to find out the best values a and b so that I minimize the sum of these squared residuals. right? And so this is a nice way of writing it because given a value x, I'm predicting a value y, right? And remember, my residual is the difference in the y coordinate. So this makes it actually a nice way to represent it here. Okay, so so I can write this now as say the L2 cost of a line with the data set and line described by A and B is going to be the sum over the points P of Py of this data point P minus A Px plus B squared. I guess that would be if I did minus B here, but so you can do plus or minus B. It's, you know, one or the other. I think okay, it's one or the other. There may be an inconsistency in my notes. I'll try and fix it after class. Okay, so this is our cost function here, measured in terms of A and B, and we want to find this minimum. Now we want to find a minimum over these two values. It seems tricky to do this, but there's a simple solution. In order to get the solution, let me define some notation. Say Px is going to be the average of all of the x coordinates of so again, this is the average. I sum all the x coordinates, divide by n. And so then I can say that the covariance between two vectors, say Px and Py, I can define this as 1 over n for Px minus Px hat. So this is the average. Py minus Py hat. Okay, so sometimes to pre-process this, you shift your data so the average point of your data is at the origin, and then these average are 0 and they kind of drop out. But then you have to keep track of this. So this is written a bit more explicitly here. And so then if you know the covariance, then the variance of just Px is equal to the covariance of Px, right? So now once I have these terms, I can automatically solve for A. Turns out A is going to be equal to the covariance of Px Py divided by the variance of Px. That solves for that's the right solution for A, and then B is going to be equal to Py minus A Px bar. Okay, so after I have A, then I can also solve for B. So B, once I have the slope of the line, you can think of I'm minimizing the sum of the squared errors, so I can just slide the line up and down until I have the average, right? And this is basically just doing the average in the y coordinates. The slope is the tricky part, but there's this nice closed form solution. So is this similar to this is kind of an extension of taking the average over how you did as the intermediate step of Lloyd's algorithm. This works for the average of the slopes. It's a bit more complicated to do this. Okay, so there's this closed form solution for minimizing the sum of the squared errors. And this is really nice. That's why people use this error function typically. But I'll mention kind of an even like another interesting kind of proof that this is kind of the right way of doing it in a certain sense. So I'm not going to go through the derivation of how you get this A and B. But let me just tell you about some extensions of this first, and then we'll talk about the optimality of this approach a bit. Okay, but this seems pretty simple, right? You could go and calculate this on your own. You know, this is built into a lot of software, but you could go and calculate this. You know, often what's built in instead is not in R2. So let me first just mention a couple of generalizations of this. So if you're in RD instead of in R2, then your data set's going to look differently. You're going to have this point set, which is going to have. So what you're going to think about is dividing it up differently. You're going to still have this special this dth coordinate. This is still going to be a vector py. So this is going to be the dth coordinate of each point is this py, and then you're going to have this other vector x. This will be a vector x here. And so what you're going to have is that you're going to have, so let's say that a point is going to be R1, R2, up to RD minus 1, then py, right? So this is a point. So if I get this, so if this is for my point P, let me do this in blue, right? So if my point P, then the py coordinate goes in this last vector here, and I get R1, R2, RD minus 1, and then I put the last coordinate as 1. So this is still has d coordinates in it. Okay, so I get this vector x, and it's going to be all these information, but the last coordinate of the last column here is all 1s. Okay, so now I have a vector py here and a matrix x, which is going to be n rows if I have n data points and d columns, and then this other column. And so if you remember, we're still going to be measuring just this vertical distance, and I separated out this py because this tells me this is the part that I'm using to measure, and this is the data I'm using to predict this measurement. Okay? And so then once I have this data x, again there's this solution where you say A is equal to, and this is written in linear algebra terms, x transpose x. I take the inverse of this, x transpose, and then py, which is a vector. Okay, so if I write this in MATLAB, it's going to give me this A. A is now going to be not just a slope, but is going to be a vector. A is going to be a d-dimensional vector now. Okay, and there isn't a separate thing for B. So A is now going to be A1, A2, up to A D minus 1. But then the last coordinate of A is magically going to be this B offset term. And by encoding all the ones in here, it's kind of it's doing that for me. Right? So this means that there's some linear system here that what I'm doing is I'm predicting. So you can think of this, people call this what's often called the hat matrix, which is x transpose x minus 1, x transpose. So this is the hat matrix, and the reason for this is that I can make some prediction of the y value by taking my data, some data point, and applying A here. Okay, so that's this extra. So instead of having this value here, so this is equal to the hat matrix x times py, right? So this part was A, and I had the x in front. So h of x py gives me my estimate of y hat. So that means given this input y here, I can get this output. Okay, and so what this is doing is I'm saying, given an input, this should be, okay, there's something, Okay, I'm going to trust my notes here. Okay. So there's this other way of thinking about this, that I'm predicting a value y hat as using this vector a as this linear system of my inputs, right? So I'm getting a1 x1 plus a2 x2 plus plus this b term here, right? So this 1 was multiplied by this b term, which I didn't have any of my inputs here. I think I might have something off here, but I'll double check this after class. So it's now a linear combination again, so it's still linear, and I'm minimizing the error from what I predicted. I want y hat minus py. I want the sum of these values squared to be small. That's what I'm going to want. Okay, so and you can solve this again in a closed form, right? So again, there's this nice solution for this. And so then once I have this in RD, this linear form, I can actually, instead of fitting, say, if instead my data looked like this, what I might want to do is to fit a polynomial curve through this data instead. I might want to say, instead of a linear line, I want to fit a polynomial curve. And now I still want to minimize the sum of these vertical distances squared to this polynomial curve, right? So let's say I said this red curve was of degree 3. If this curve is of degree 3, it means that I can write this. Let's call this a curve. I can write the curve of a value x should equal to a1x plus a2x squared plus a3x fourth plus b. Right? So I can write it as, sorry, this should be third. Okay, so I can write it as this polynomial function here. And so the trick is that I can again solve this using this higher dimensional linear system by saying that the first coordinate is going to be x. The second coordinate is x squared. And the third coordinate is x cubed. Okay? So now even if I only have, if I'm predicting the value of this data point, I want to predict it on this line. What I do is I first take this data point and I map it to a three-dimensional point. Right? So I go from x to this three-dimensional point, x squared, x cubed. And now I can solve this linear system again on these higher dimensional points. Right? So what I would like to do is I would like to find this y hat, which is going to be equal to b plus a1x plus a2x plus, in this case, a3x, right? But you could make this a sum longer if you wanted a higher dimensional polynomial, right? So this would be, if I set this equal to a0, then this would be the sum over I equals 0 up to some t degree polynomial of ai times x to the power I. And x to the 0 is going to be 1, so it kind of satisfies this. Right? So now, as my input matrix, now I have this input matrix x. And so if I have for a value p, if I have px, this was px, this is px squared is the second coordinate, px cubed is the third coordinate, and 1 is going to correspond to this b here. So I can take this linear solution in higher dimensions and use it to solve for these polynomial curves as well. Okay, so and it means that if this linear system was the closed form solution for that, then I also have a closed form solution for fitting these polynomial curves. This is the solution I get out of here with these coordinates. These coordinates is what I'm solving for. If these describe this curve precisely, and it's the least square, so it's the one that minimizes the sum of the square distances. So I can again solve this exactly in closed form for any fixed degree polynomial curve. Okay, so this is really cool, right? So if this is what I want to do, I want to minimize the sum of the square distances, the vertical distances here. Then I can have this closed form solution by using this linear algebra trick. Okay, and so in fact, there's this theorem called the Gauss Markov theorem. Okay, and so this says that the linear least squares solution. Is the minimum variance solution, and the minimum variance means it minimizes the sum of the squared errors. That's what minimum variance means. So if I make two assumptions, is the minimum variance with the first assumption meaning that the solution has zero expected error. Okay. Oh gosh. Okay. Got too excited about that error. So the minimum has zero expected error, which means it has no bias in the solution. So that means that if under some randomness model, the expected value of y hat is equal to py. So it's not going to be the right thing, but if there's some error that's generating the data from the true model, that the expected value of y hat is going to be exactly this value py that I got, right? And this is under the assumption that all errors, say, where I define this as this residual, say px minus a, so py minus a px minus b. So if all these errors are not known to be correlated. Okay, so if there's no known correlation between the errors, so I don't know anything, I just think every data point came from this model I'm predicting, some A model defined by a line A and B, and this generalizes to the higher dimensional polynomial settings. And I want my solution to have no expected error. So I take in some based on the data I have, and I predict the value y hat based on the data I have, and based on my model, I expect it to eat the right thing. So I want it to have the right expectation. If these are true, then this is the lowest variance solution. There's nothing better I can do. Okay, so it seems like if this is the case, then then there's nothing else to say on this topic, right? That maybe we can stop here, and maybe I'll, after I check the notes and make sure I didn't make a mistake there, we can then take the next few lectures off, right? But why is this not the end of the story? So this is great, right? If you want a minimum variance solution with no expected error, and you don't know anything about some weird correlation in the data, then you can't do any better than this, right? But why would you sometimes want to do something else? Yeah. So if you have outliers, well, yeah, if you have outliers, this is still the minimum variance solution. as long as you have if you have no expected error.
If your points are not evenly positioned around the regression line.
So they're not evenly.
I'm trying to think of the exact word for it. It's like,
Yeah. So there's one thing there's one issue with outliers. Okay. So you're onto this. You know, we looked at this is measuring the sum of py minus the line. You know, so you're predicting the sum of the squared errors. This is what the variance is. And this is one choice of error measure, just like you're going to do in the homework, hopefully. You know, you're going to do the k-mean solution, which is nice and simple to do, and then I ask you to do this k-median solution. And I do that because that's more robust to outliers. This is the squared distance. So if you have an outlier, you're saying not only do I count the distance of the outlier, I'm taking that distance and I'm squaring it. So the really far away points with the large residuals become even more important than close points. You're saying the outliers are more important here. So it's not very, very robust to outliers. So the linear least squares is not robust. Okay, so we'll talk about a couple ways of making this more robust. One way does not one way is going to explicitly add bias. The other is not going to explicitly add bias. So one is kind of like taking the median instead of the mean. The other one is, the other thing is we may want to add bias. This sounds strange, right? But this was assuming that there was no bias in the solution, right? This says this is the minimum variance solution, assuming I had no bias. Why did I have to assume this? Is it possible I could have a lower variance solution if I added bias? That means that I know for some questions I'm not going to get the right expected value. Is that possible? Well, this theorem says it could be possible. And so it turns out that this is the case. You can add bias to your solution, and you can get you can make a prediction y hat that on average has smaller squared error. Okay, some things you're going to say I'm probably going to be not going to have the right expected value on this, but overall I'm going to have smaller squared error. Which is kind of strange, but we'll go through and see why this works. And you can actually write it down in 2D, but it'll really make more sense in higher dimensions. Yeah.
So do you mean it's not minimizing the variance, but mean square error?
I am minimizing the variance, but I'm not restricting that I'm unbiased.
Oh.
So if you allow bias, you can have smaller variance solution.
And also, is there any quantification for robustness?
Yes, there is, and we'll cover. I'll preview each of these in the rest of the lecture. Yeah. So smaller. So by adding variance, I can get smaller variance. Yeah. What's another thing? If we go back here, I said this minimizing the sum of this vertical distance here, right? What if I want to minimize the sum of the closest distance? So residual equals projection distance, not the vertical distance, right? So you know, if I minimize that instead, that seems maybe that's more natural. Maybe that's getting a better fit. This is explicitly modeling just the vertical distance. Okay, so we'll talk about this. Doing the projection distance instead of the vertical distance is actually pretty dangerous and is often abused. In some ways, it gives more natural fit. And so we'll talk about doing PCA next lecture on Wednesday. And that's all about doing this. The thing is, it treats all the dimensions the same, which is sometimes good, but sometimes doesn't make sense. If they have different coordinates, this gets you into trouble. But the vertical distance is a very natural thing. You pick which of the coordinates you care about minimizing as your prediction, where PCA does not do this, right? But it doesn't need to be the vertical distance. It could be that projection distance instead. And then finally, the last thing we'll talk about here is we can make this faster. So particularly in high dimensions, this operation, when I take this inverse here, this can be slow. So I may want to do something to kind of allow me to speed this up. Maybe not explicitly. I may do something where I kind of compress the data, and then I do this on a smaller data set instead of on the full data set, something like that. So I can make faster with some approximation. Okay, and so we'll talk about this. So this is what we'll talk about next week. Yeah, question.
Take a step back. Could you please clarify on the bias? Having a bias means, does it imply that the points are drawn from a noisy distribution?
Well, I'm already kind of assuming that. There's some assumption here I didn't go through explicitly, but you assume that all the values y were you started with the value x, you used this model, and then you added some noise here, right? And you assume that these were uncorrelated. Each one was drawn in IID.
Yeah, so can you give me an example when there would be bias?
Well, no, I'm not saying there's bias here in the noise. I'm saying our prediction will be biased, and this will all go through soon. So I'll give an example of how to do this lecture, and then in a later lecture we'll see kind of why it makes sense, and in some more detail. So these are kind of some ways that we can extend this. There's also something I didn't explicitly list here. So sometimes you have, we're gonna, and it kind of fits within this adding biased and sometimes faster, is there's this family of kind of this new area that's called compressed sensing, and the idea is that sometimes your solution to this, if you make it sparse, meaning that it only makes sense in high dimensions, so it'll be a while before I fully explain it. But you want, if you look at these, if you go back here, if you look at these, if I have a really long linear combination, I want a lot of these coordinates in these A to be 0, so I don't have to worry about multiplying this out. And sometimes the sparse solutions kind of are better in some ways. Sometimes your data initially is sparse plus some noise on top, and you can actually recover a solution which kind of biases it towards being sparse, which ends up being better. And this has some nice, various nice applications that we'll talk about. Okay, so there's lots left to do beyond linear least squares. Okay, so let's kind of give a preview of these. So the first one I'm going to talk about is what's called the ThielArms Sen estimator. And so this is going to be a way of making this more robust to outliers. Okay, so there's this area of statistics that's called robust statistics. And so the idea is that you want to, if you have outliers, you don't want your what your prediction is to change very much. You want to be robust to outliers. So there's kind of the formal way to define this is what's called is what's called a breakdown point, and the idea is and so there's kind of a very mathematical definition, and I'll say it in words without defining what everything means. But it says that I'm gonna have some estimator that's based on my data, and I say that if let's say an f fraction of x moves to so it moves to infinity. It moves arbitrarily far away. So these are really bad outliers. Then phi hat of x does not move to infinity. Okay. Then if this is true, then f. So if the maximum such f, the maximum f is the breakdown point. Okay, so just to go through an example. So if you're calculating, so the classic example of this is if you look at the mean of a point set or the average, right? So just the one-dimensional average. I've got points here, and I want to compute the average, which is what minimizes the sum of the squared errors, the variance that we want. I take 1 point and move it out here, then it moves the average out to here. And if I move this out to infinity, this average moves to infinity as well, because this is, I compute this as 1 over n of the sum of these data points. So if 1 goes to infinity, the average goes to infinity. This is very susceptible to outliers, where if I take the median instead, I have points like this and 1's out at infinity, the median is still out here. And if I move n over 2 of the points, if I move half the points minus 1, almost half the points to infinity, right? So n over 2 minus 1 points are here, and n over 2, say, plus 1 points over here. The median is still over here. So I can move half the points out here. So this is very robust to outliers. Okay, so now the question is, how can we do something like fitting a line through data, but getting properties of the median instead of the mean?
Well, my question is, if half of the data is way out there, then can they be really considered an outlier?
Yeah, okay, yeah. So if half the data is out there, then that's great. So, right, so the median has a very strong property that the breakdown point, f is equal to 1/2. This is as strong as you can get. It's actually the infimum instead of the max, right? It's what you technically want to write here. But other sort of things have a breakdown point of, say, 0.29. The ThielArms estimator has a breakdown point of 0.29. That means I can move up to 1/3 of the points out to infinity, and it still stays robust. So it's not. Yeah, so if half the points are out there, then I probably shouldn't be fitting it this way because I'm doing something wrong. That's when I want to do clustering instead, probably, right? Then there are two with 2 centers, right? So yeah, it's not saying I should fit it this way, but I'm saying even if half the points or 30% of the points are outliers, I still am getting a good fit, right? So if I get something like a breakdown point of 10%, that's already pretty good. I can have 10% outliers. But it's just kind of a notion of some of these estimators are stronger than others because they have a better breakdown point. Okay, and so the ThielArms estimator is one of these ways, and so it's the ThielArms estimator, and so it's basically just applying the median to every step instead of instead of doing the mean, and so basically what I'm going to do is I'm going to take all my points, all my x coordinates. So I'll call these x1, x2. So this corresponds with p1, p2, up to xn. This is pn, and we'll assume they're in sorted order. And so I'm going to calculate a bunch of these slopes, Sij, which is going to be the slope, and this is yj minus yi over xj minus xi, and I calculate this slope if xi is less than xj. Otherwise, I calculate sji instead. So I only calculate between 2 points. If xi is here and xj is here, then I'll calculate this slope. Otherwise, I'll get a value which is negative. Okay, so I take all of these slopes, and I'm going to let a equals the median of this set of these Sij, of all these slopes. So I calculate all the slopes of pairs of points so that it's either increasing or decreasing, and then I take the median of these, right? And then in order to get b, I'm going to take again the median of yi minus a xi, right? So I'll create this set for all the data points. I'll look at where it intercepts the y-axis, and I take the median of those. So again, I'm just replacing kind of these steps where I was kind of doing something like a mean before, and I'm replacing with the median. And this gives a solution which is more robust. It's again a line that fits the data, and it has a break down point. I think it's 0.29, something like that. So I can have like 29% of my data be outliers, and it still gives me a pretty reasonable solution. And then so this is one way of doing it. This is actually more popular. But then there's an extension by Siegel, which is instead of doing this step for the median, it's actually looking at it's instead saying that let's say Si is going to be the median of Sij union Sji. So for every data point, so this is Xi, I look at all the other points. They could be down here, and I get all of these different slopes, right? And so I'm going to get one slope that should go through there, okay? Pretend that blue line went through there. And this is slope Si, and then I'm going to set A equals the median of all these Si's. Okay, and so if I do this and then I get B the same way, if I do this version, it's going to have a breakdown point of 0.5. So this is optimal, the optimal breakdown point. So you can do this instead, and you can actually do this in just as fast as sorting time if you're a little bit clever. And this is going to be more robust outliers. There's another form which is called that I won't talk about, called I forget what it's called, but you can just minimize the sum of the distances instead of the sum of the squared residuals. And there's not a pretty solution to that. You can kind of there's convex, so you can run an optimization procedure like gradient descent or some extension of that, and that can find something that minimizes the sum of the errors as well. And that also is robust outliers. Okay, so these are just some other initial ways of thinking about extending it. This is all I'm going to say about these robust statistic view of this. The other way that I think is more interesting is where I'm adding bias into the solution. Okay, so now let's talk about adding bias. And so there are two ways we'll talk about doing this. The first way, which is easier to implement, is called Tikhonov Tikhonov regularization. Okay, or as a lot of people call it, just ridge regression. So Tikhonov is probably, I think, Russian, probably, and so I think he was probably one of the early people to come up with this. And so this is the way you're going to add bias into your solution. And now the goal is we're going to minimize instead not just the L2 error in our solution. We're going to add some extra parameter S. So given a data point P and a slope A, and so I'm going to ignore this B term. I'm going to assume that I started by taking all the y coordinates and setting all these to 0. So let's assume Py equals to 0 and Px equals to 0. So let's just assume these. If not, you can extend it. But just to write this down, we're going to minimize this cost function instead, which is the sum. Okay, is going to be sum of Py minus A times Px. Okay, this part looks familiar, but I'm going to add a term, and this term is called this is called a regularization term, and it's going to be S times A squared. Okay, so this is called a regularization term. And so because I'm solving for this with this added term here, my solution is going to be biased. It's not just the sum of the squared errors, it's also minimizing this function here. And what is this saying here, right? It's saying S is some parameter, which I'll talk about in a little bit, and A squared. A was my slope. Okay, so I'm saying I want to minimize this, so I don't want to have a large slope. So this is a bias to small slope. As the slope gets further away from 0, I'm adding more penalty. Okay, and so this is, regularization term. It's also sometimes called a shrinkage term, because I'm essentially shrinking the slope in my solution. So I'm shrinking this. Okay. So the kind of we'll talk a little bit more about this when we I'll have a full lecture on kind of extending this in higher dimensions and the meaning and how this relates to compressed sensing and certain things. But the idea is, if you have an outlier, you're assuming the x coordinate is fine, is right, but the y coordinate is all messed up. And if it's all messed up, it's really bad. We only care about outliers if they're really far away from the data that we're predicting. That means our outliers are probably either very close to positive infinity or very close to negative infinity. Either way, they're really driving the value of the slope. Okay, so I want the slope to be close to 0 because I've centered it to start with. And to uncenter it, use the same trick where you go to the higher dimensions and you put all the ones, and then so you can kind of get rid of this. You can get rid of this assumption. But I'm saying that outlier is probably going to pull the data so that the slope is too high. And so we want to say, if the outliers are doing that, then let's bias it to have a little bit smaller slope than we would have predicted. And this will work against the outliers. And so kind of, so we'll talk a little bit more about this, but there's a dual version of this called where instead of minimizing this function, I want to minimize a different one that has the parameter t, so PA, which is going to be the sum of P py minus a px. This is the same. But now I'm going to say such that I'm going to, under the condition that a squared is less than t. Okay, so I'm still minimizing this exactly, which is what I wanted, but subject to this condition, that my slope, my squared slope is less than some upper bound. Okay, so I can do this instead. It turns out that for every value s, there's another value t where these two, minimizing either of these, gives you the same solution. Okay, so as I decrease s, this is less important, I'm essentially increasing t. So then what I'm saying is I'm finding the same least square solution, but I'm just not allowing slopes that are really big. I'm saying if the slope gets really big, I'm like, I don't trust this anymore, right? So think about if your data goes through the origin, right? And your data, was kind of like this, but there was some point way up here, and so it made this, so I had my line go through like this. I'm not going to trust this. As the line gets really vertical, the predictions are all getting really big. I'm saying this line's not telling me much. The line tells you more as it's flatter. It's kind of saying, if it's too vertical, there's a lot going on. I move x coordinate a little bit, I get a really big change. This seems not very stable. So I say I'm not going to allow slopes that are too big. And so I can say I can have any solution I want as long as the slope's not big. And so these are equivalent. These two formulations are absolutely equivalent to each other. So this maybe makes a little bit, maybe this one seems a little bit more reasonable. But this one, it turns out, is easier to solve. It turns out I can solve a hat, and I'll write this down in as there's a closed form solution again. So it's just like so it's the same as before. This was a closed form solution without the regularization term s here, but then I just add an s squared here in the bottom. So in order to solve this with adding this bias, I just, in my solution for A, I just add this s squared here, this term inside the denominator, and you can extend this to the matrix case, the higher dimensional case. This is XX transpose plus S squared times the identity matrix. You take the inverse of this, X transpose PY. Okay, so I can do this same solution here. Now this gives me a vector, but it just goes inside of this inverse. The inverse is like dividing by something, right? So the solution is just as easy, basically, as the least square solution, but often it will give you, it will handle these outlier points better. Okay, so maybe this still, and the extension there is instead of A, you use, you take the norm of A squared in place here. Okay, so we'll talk about this a bit more of why this works and why it betters. It's better, but it actually, if you choose, there's this just like there's this Gauss-Markov theorem. There's a theorem that says if you do ridge regression with the right value s, if you choose s correctly, then the variance, then there's a solution here that gives you a variance that's better than the linear least squares. This will always give you as good or better. Okay, and the case when it's as good is just setting s equal to 0. So that's not interesting. But it turns out that's only the case where there's no error at all. You only would get s equals to 0 is the right solution when there's no error at all in this. So unless there's no error, you can always do better using this ridge regression instead of just least squares. The problem is you don't always know what the right value of s is. Okay, so this becomes a little tricky. What you want to do is you'll take your data and you'll leave some of the data out, and you'll build a model on, say, 90% of your data, and then you evaluate the error on the other 10%. And then you find the value S that has the least error on the other 10%. So you try a bunch of values S, and you can usually do you can usually do like binary search on S, and you can find the value S which minimizes this the error on the data that you've left out. And so this is kind of interesting because the goal for this is to kind of predict if you had a new piece of data. If I have a new data point that's coming in, I want to predict where this data is going to be. If I just have the X coordinate, I want to predict the Y coordinate. And you're probably better off if you had a line here. It's more likely you're going to have less error if you predict it here than if you did up here. If you had a new green point, you would think it's probably going to be here instead of here, and even though this is the best least square solution. So that's kind of what's going on. So that's kind of an and this is just as easy to do, and it can give much better bounds. But you just have to kind of experiment to figure out what the best value S is. Okay, so there's there's another version of this that maybe some of you have have heard. That's either called the lasso, which is like lassoing a horse. So in Utah, maybe, has anyone here ever lassoed a horse? Yeah? Okay, one person. Cool. So how many people have been to a rodeo? I've seen someone do it. Okay. So a rodeo is a really cool thing if you haven't been. Especially the smaller rodeos, like the one at the basketball stadium is not. You should go to like the small town rodeos. Okay, so it's also sometimes called basis pursuit, and that's going to be similar here. Is going to be you're going to calculate the error as the sum of P and P of Py minus A Px squared plus S, and now just times the absolute value of A instead of A squared. Okay, so this one turns out this one actually tends to work a little bit better in higher dimensions. It's going to be more robust, and it's going to give this sparsity in the solution. It's going to bias towards sparse solutions, which will be really cool and useful in some ways. The problem is there's not a closed form solution. There's not, so we can just take the inverse, set it up, and take the inverse. We can't just solve it. We can't just solve it the way we did before. There's an algorithm to solve for this. So there are an algorithm that I'll describe where you kind of do something like dynamic programming, and you can solve for the solution to this for any value S. And in fact, it solves for all values S simultaneously, so you can do the cross-validation to figure out which value S is better while you're actually calculating it. But it's a bit more complicated. So we'll talk about this later. And then we're running out of time, so then the other thing is PCA that we'll have a lecture on. That'll be on Wednesday. And this is PCA means principal component analysis. And again, we touched on this idea with spectral clustering, but this is doing dimensionality. So this is doing dimensionality reduction. And so when you're in 2D, this is the solution that finds the errors in the residual on the projection onto here instead of the vertical distance. But in higher dimensions, what this is going to give you is the best low-dimensional approximation of high-dimensional data. Okay, and so we'll talk about how this works. And this is kind of the first tool you should use whenever you have high-dimensional data. if all the data points have the same kind of have the same units on the axis. Okay. Okay. So I'll post some extensions to the homework on Canvas this evening. Now due Saturday at midnight in case you missed it.